Good morning, everyone. I hope you're all doing well. Thank you, organizers, for giving me the opportunity. My name is Anisha Harshan. I'm a final year PhD student at the University of New South Wales. And today I'll be talking to you about the beginning of the end for massive protocluster galaxies at redshift of 2 and why environment matters. So we've known for a while that environment affects the star formation rates of the galaxy. And we've seen that especially in the local universe, as is shown here. The cluster galaxies, which are in the red shaded region, have declining star formation rates as we go closer to the cluster center, whereas the field galaxies, which are in the blue shaded region, have a stagnant star formation rates irrespective of its proximity to the cluster center. So the environment can affect star formation rates of a galaxy due to various different mechanisms. Either the gas of the galaxy is stripped off of the galaxy due to gravitational interactions with other galaxies, or the intracluster medium, or the galaxy is not able to form further stars because of its own internal feedback mechanisms. And we know that the effect of environment on star formation and other ISM properties are becoming significant enough and observable at the redshift of 1.5-ish. And that has been shown in both observations and simulations. As is shown here in a redshift 2 protocluster, the star formation rate of the galaxies, which is shown on the y-axis, for cluster galaxies, which is shown in red, are slightly lower compared to the field galaxies, which is shown in blue. And we also find in a previous work that cluster galaxies, especially in the low mass end, have slightly elevated electron densities compared to the field galaxies as well. And electron density, as we know, is dependent upon the star formation rate of the galaxy, as well as the gas inside the galaxy. So we have reasons to now believe that environment is affecting the star formation rates of the galaxies as early as redshift of 2. So to dig a little bit deeper and to look at when the star formation history is being affected, we are going to look at a protocluster at redshift of 2, which was first identified in the ZFOG photometric survey, and then later spectroscopically confirmed to be between 2.08 and 2.12 redshift range with the Z5 spectroscopic survey. Now, the ZFOG photometric survey has 5 medium band near-infrared filters, and because these galaxies are in the cosmos field, it has a wealth of legacy data with 32 other photometric bands. So with the rich photometry from ZFOG and along with the spectroscopic redshift from ZFIRE, we can fit the SEDs of these galaxies. And to do that, we have used an SED fitting code called Prospector, which will give us nonparametric forms of star formation histories. Now that we are equipped with our SED fits and the star formation histories, we can start to analyze them. We have divided our sample into 4 stellar mass bins, and the lowest being the 9 to 9.5 log solar masses. We have divided the galaxies into the protocluster and field environment, depending on the spectroscopic redshifts. And we have given the prospective 5 age bins to get the star formation histories, which is now shown on the y-axis. That is the star formation rate for each age bin, divided by the stellar mass of the galaxies at the time of observation. And the x-axis is now the age of the universe, such that the right-hand side is towards Big Bang and the left-hand side is towards the time of observations for these galaxies, that is at redshift of 2. In the lowest mass bin, we find that the protocluster galaxies, which are shown in red, have very similar star formation histories to field galaxies, which are shown in blue. But the star formation histories for lower stellar mass galaxies is a rise in star formation history. That means that galaxies are only starting to form stars now. As we go further along in the stellar mass range, we find that the rise in star formation history that we saw earlier has been now changed into a bursty star formation history. But again, there is no significant difference between the protocluster and field galaxy star formation histories. As we go further along, we still see very similar star formation history between environment and the star formation histories are still bursty, but cluster galaxies are now starting to form a bit more stars compared to the field galaxies in the earlier stage bin. And it is only in the most massive bin that we find any significant difference between environment, such that the cluster galaxies now have a very flat star formation histories compared to the field galaxies. Cluster galaxies are also forming significantly higher stars in the last age bin. That is that they are forming much more stars much more earlier. So now to summarize this result, we see that cluster galaxies and field galaxies only, the effect of environment on star formation histories is only significant in the most massive bin, and we see effect of sort of galaxy downsizing. Now that we have star formation histories from observations, we can look at cosmological simulations. And to do that, we have used Illustris TNG. We can use Illustris TNG to select each galaxies in different different environments and stellar mass ranges, as we've done for observations. We can track their evolutionary histories as well as star formation histories, and use TNG to really try to understand what is actually driving the star formation histories. So we've done exactly that, and I have summarized that plot here. We can see now the cluster galaxies are shown in brown, and the field galaxies for TNG are shown in field. Sort of a teal. And we can see that the lowest stellar mass bin, as shown in this first plot, have a rising star formation history. And as we go further along in the stellar mass bin, we find that the cluster galaxies and field galaxies have a rising star formation history, but then they are starting to stagnate. And as we go further along in this plot here, we see that the cluster galaxies and field galaxies have a, sorry about that. We again see that the star formation histories are sort of rising and then stagnating, but the constant star formation histories, stagnation happens much earlier compared to the last stellar mass bin. And again, as we saw in observations, we only see that the effect of environment on star formation histories is only prominent in these most massive stellar mass bin, such that the cluster galaxies now have a declining star formation histories compared to field galaxies, which have a rising and a constant star formation history. Now, this result is qualitatively comparable to the results that we find from observations. And so now we can use TNG to understand what is causing the difference in the star formation histories in the most massive bin. Because we are finding that the difference is in star formation histories is only in the most massive bin, first question to answer is the nature versus nurture debate. So did the massive protocluster galaxies simply form earlier, and hence they have evolved and are quenching earlier? So to do that, we have looked at the mass-weighted stellar ages of these galaxies, which is now shown on the y-axis, and the x-axis is the stellar ages of the galaxies in the 4 stellar mass bins that we had defined earlier. So to answer the question, did massive galaxies form earlier? Yes, about 190 million years earlier compared to the lowest mass galaxies. But did cluster galaxies form earlier than field galaxies across stellar mass range? That is not the case. Even in the most massive bin, the stellar mass-weighted stellar ages are within 1 sigma uncertainty. So the driving force of the star formation histories difference is not simply the stellar ages or the formation times of these galaxies. Now, then we need to look at how environments shape the star formation of these galaxies. One of the ways that environment does this by mergers. And so we have looked at the total distribution of major and minor mergers that these galaxies are experiencing till redshift of 2. So we can see that in the most massive bin, so the stellar mass range goes from lowest to highest, from left to right. And in the most massive bin, we find a slight difference between the mean number of mergers that these galaxies are experiencing, such that the cluster galaxies are having a slightly higher number of mergers than the field galaxies, but the overall distribution is still very same. So we do not think that the mergers are the driving force of the difference in the star formation histories for the most massive bin. So then we are going to look at the total gas fractions of these galaxies. We are now looking, so the total gas fraction of progenitors, which means just all the gas that is available for the galaxy to form stars in the entire history of these galaxies. So y-axis is now the total gas fraction of progenitors, and x-axis is again the age of the universe. Towards right-hand side is towards Big Bang, and towards left-hand side is as we go towards redshift of 2, which is the time of observations for these galaxies. What is plotted here is the lowest stellar mass bin, and we do not see any significant difference between the total gas fractions of progenitors in this mass bin. And as we go further along in the stellar mass bin, the difference between gas fraction is starting to appear, but it is appearing much later. As we go further along, it is only in the most massive stellar mass bin that galaxies are having much lower total gas fractions in the progenitors, such that the cluster galaxies are having lower gas fractions as early as 1 gigayear of the universe. So we think that the difference in the star formation histories that we are finding here, both in observations and simulations, is probably being driven due to the fact that these galaxies have lower gas fractions as early as 1 gigayear of the universe. And for some reason, these galaxies are not even able to form, to get more gas from its environment, despite being in very gas-rich environments. I will summarize the talk now. Both in observations and simulations, we are finding that most massive protocluster galaxies are starting to quench. And we do not think it is a result of early formation and evolution of cluster galaxies, because they have very similar mass-weighted stellar ages. And we think it is probably because of the low gas fraction of the progenitors of massive protocluster galaxies that are having lower flatter star formation histories that we are finding in both observations and simulations. You can read the paper that is on arXiv right now. It has been accepted as well, so please read it and I'll take any questions.
Okay, thanks, Anisha. So there are many questions on Slack. So let's start from the Katie's one. So she asked, how important is the role that mergers play in shaping the star formation history? Do simulations reflect the observations?
So we cannot pinpoint one particular, at least in observations, we have not been able to do that. Like attributes difference of star formation histories to just mergers, but there have been papers within that use simulations that show that mergers of different kinds are having a significant effect on the star formation histories, or just the star formation rates of the galaxies. And that depends on the mass ratio or the gas ratio of the galaxies, and also on the fact that if the galaxy is actually forming stars or not.
Good. So time's already almost up. Just take one more question from Scott. So he asked, the simulations don't seem to show the same level of short timescale burst compared to the data. So what do you think is causing the apparent difference?
Sorry, can you repeat the question? Can I get it?
Okay, so he asked, the simulation don't seem to show the same level of short timescale burst compared to the data. So what do you think is causing the apparent difference?
So the bursts are also there in simulations as well, but the thing that it's not coming up in the plots that I've shown here is because the number of galaxies that are in simulations is much more than observations, so the bursts kind of get the effect of burst kind of becomes flatter because they are on different times for all galaxies. And I think that's probably why we do not see that much of a burst effect. But if we look at the present stuff, like just the stellar mass distribution of the present time galaxy, even in Illustris, we find very similar results as we saw in Prospector. So that's great news.
Okay, thank you, Anisha. So there are plenty of questions on Slack, so please check it. And thanks again.